Good evening, everyone. So today is the sixth live problem session for NPTEL course of Communication Networks. So today we will be covering the topics that have been taught in week 6 of NPTEL Communication Networks. We will first go through the basics of the topics, and then we will, after going through the basic concepts, we will try to solve some problems based on those concepts. So today we will be mostly talking about two things. First, we will talk about MM1 queues, and then we will talk about network topology. These are the two topics for today: MM1 queues and network topology. So the first we will go through MM1 queue, then we will learn about the various network topologies, and then we will solve some problems. So MM1 queue, we have already talked about general queuing theory, arrival time, inter-arrival time, Poisson distribution in the previous 2 weeks. So this week we will be focusing on a specific type of queue called the MM1 queue, where you will have Markovian distribution, so a Markovian process, so exponential interarrival and Poisson distribution of arrival. So let us start without further ado. So to know what is MM1 queue, first we will go through the very basics definition of MM1 queue. So in MM1 queue, there is a service node which services the packets, and the packets come at an arrival rate of lambda, and they are serviced at a rate of mu per second. So mu is the rate at which they are serviced, and lambda is the rate at which the packets are arriving. So after arrival, if one packet arrives, they will of course wait at the service area, and if more than one packets, they will go to the service area. If more than one packet arrives, then there is the concept of waiting, because a single queue, a single server cannot handle one more than one packet at a time. So the packets that come while a current packet is getting serviced, those packets are sent to the waiting area. So arrivals occur at a rate of lambda according to Poisson process. Service times have an exponential distribution. So arrivals occur at rate lambda. So MM1 queue, what are the definition? So MM1 here, 1 means there is only one server. So this is the meaning of 1 in MM1 queue. So in MM1 queue, the first M talks about the arrival, which is in Poisson, or you can say or exponential array. Exponential interarrival. So a Poisson arrival or exponential interarrival. This one talks about the service. So the service time is again exponential. And this one talks about the number of servers. This one is the number of servers. This depicts the number of servers. So we have arrival as Poisson lambda, or this can be alternatively written as interarrival is exponential lambda. Poisson interarrival is EXP lambda. Interarrival is EXP lambda. So this is the first M. The second M means that second M means service is EXP mu. So service is exponentially distributed with rate parameter mu. This means second M. And 1 is just the number of servers. So there is only a single server. Okay. So arrivals occur at a rate lambda according to Poisson process. Service times have an exponential distribution with rate parameter mu. All arrivals and service times are independent of each other. So all packets arrive independently of each other and they are serviced independently of each other. And a very important assumption, the buffer is of infinite size. So there is no limit of customer it can contain. So this buffer, this waiting area is infinitely large. So as many packets are coming, they are all welcomed. No packet is getting rejected. So if the buffer is like limited, then once the buffer becomes full, some packets might get rejected. Here in MM1 queue, no matter how long the waiting time, all packets will get serviced because there is an infinite buffer for queue. So all packets will get serviced. So, but if you come, of course, if you come late, you will not, you will not get your, and you will not get your, what to say this. You will have a very long waiting time, but ultimately you will get serviced. So this can be compared to a train station platform. So in a platform, you will see ticket counters are there, and there is only one service node, that is the clerk, the cashier who is sitting at the railway ticket counter. And then there is a waiting area that is just in front of the counter, and people queue there. So people come in, people start waiting in queue there. And the thing is, railway stations are open 24 hours, right? So there is no queue limitation. No matter how long the queue is, everyone will ultimately get a ticket. Yes, the thing is, you might miss your train if you wait for a very long time in the queue, but you will get a ticket. That is guaranteed. So this is a infinite queue. This is a finite queue. Now the same thing happen. This is an infinite queue. Now if you have a finite queue, suppose in a doctor's chamber, there the doctor will see only 40 patients for the day. So he will after 40 people are waiting in queue, the 41st person will simply not get to see the doctor. So that is a finite queue. But this is an infinite queue. MM1 is an infinite queue. So the buffer is of infinite size, like a railway station ticket counter. And a single server serves customers one at a time from the front of the queue according to a first come first serve basis. So the queue system is also specified. The service system is first come first serve. When the service is complete, the customer leaves the queue and the number of customers in the system reduces by 1. So if you do a Markov chain modeling of this, you will see that the Markov chain comes like this. So the thing is, you will have here, this is a birth death process. So the first packet arrives like this, and then there is a death, and then there is another arrival, and this is the waiting, and then death, arrival, waiting, death. Death means getting serviced, arrival, waiting, death. Like that, this transition matrix is changed. Transition matrix is designed. Now, If you look at the MM1Q, there is some analysis that can be done on the MM1Q. Wait. Huh. So this is the MM1Q that you can see. This is the textbook that has been suggested to you. This is Kleinrock, Leonard Kleinrock queuing theory. So first there were no customers. Then one customer arrives. So the number of customers in the system is 1. If another customer arrives, the number of customers in the system is 2. If another arrives, then 3, like that. But if one customer gets serviced, it will get reduced to 0. If there were 2 customers and one completes his service, it will get reduced to 1. So this is the transition diagram for a MM1Q. Now, if now according to this derivation that you can do, the thing is this, for the kth state, the probability that the queue will be in the kth state, that is the probability that there are k customers waiting, is given as pk equal to p naught into k times you multiply lambda by mu. This lambda by mu you multiply k times. So you multiply this lambda by mu k times and you will get pk equal to p naught lambda by mu whole to the power k. So so p naught is the probability, ground probability, and for the first, for the kth system to be in the kth state, not the first state, for the system to be in the kth state, the probability is p naught into lambda by mu whole to the power k. Now the problem becomes of finding this p naught value. So if you do a if you do a summation of this the probabilities, you will know that this probability, the summation of these probabilities has to be 1. Okay, so the and the thing is, this summation has to converge. If this summation has to converge, this will go to infinite. The sum of these probabilities will go to infinite if this does not converge, if lambda by mu is greater than 1. So if lambda by mu is greater than 1, here in MM1Q, MM1Q, so 0, you give one birth, it is lambda, you give another birth, lambda, k, lambda, and similarly it will get reduced by 1 if it is, if one death occurs or one service gets completed. So this is mu. So the probability that system is in state k, that is there are k customers or k packets in the system. What is the probability? The probability is p naught into pi k equal to 0 to I minus 1 lambda by mu whole to the power k. Sorry, I equal to 0 to k minus 1 lambda by mu whole to the power I. So you multiply k times lambda by mu. So p naught lambda by mu whole to the power k. Now This is pk. Now pk has to, the summation of all the probabilities has to converge, because these are sum of probabilities, so they cannot go beyond 1, so they have to converge. So they have to go to a finite value, that is summation k equal to 0 to infinity pk is finite. If it is finite, that means lambda by mu has to be less than 1, or else it will not be finite, because it's a geometric series, and in a geometric series if the common ratio is more than 1, it will not converge. So lambda by has to be nil, or lambda is less than mu. So this means for the q to be sustainable, lambda should be less than mu, or arrivals should be lesser than arrivals rate should be lesser than service rate. So if service rate is basically the rate at which the server can handle the customers, so if the arrival rate is greater, so the queue will have customers who will not get service, so they will wait and they will wait and they will wait, so and other customers will come, they will also wait. So ultimately the queue will not converge and the queue will go to infinity. So to prevent that, the arrival rate should be less than service rate for convergence, or rho should be, lambda by mu should be less than 1. So we denote rho equal to lambda by mu. Rho is defined as lambda by mu is less than 1. Now this we will now derive the number of customers or number of packets in the system. Sorry, average number of packets in the system. The number of packets is basically the state. So if it is in state 0, that means there are 0 customers. If it is in state 1, that means there are 1 customer or packet, whatever you say, there are 1 packet. So if there are 2, it is in state 2, that means there are 2 packets. One is probably getting serviced, another is waiting in queue, and so on. So the average number of customers will be just the average of all the states. Average number of customers is the expectation of all the states. So n bar is equal to summation kpk. K varies from 0 to infinity. Now this will simply be summation k equal to 0 to infinity k lambda by mu whole to the power k into p naught. Now what is p naught? P naught's value has to be derived separately. So the p naught should be, how will you derive the value of p naught? Simply by stating that the sum of all the probabilities pk's should sum up to 1. If the sum of all the probabilities do not sum up to 1, then it's not done. So summation k equal to 0 to infinity pk should be 1, because the all the states together form an exclusive set. So the system has to be in one of these states from 0 to infinity. So summation k equal to 0 to pk is equal to 1. So this is p naught plus summation k equal to 1 to infinity pk is equal to 1. It implies p naught plus, now we know that p naught pk is p naught lambda by mu to the power k. This is an important formula. Pk is p naught lambda by mu to the power k. So on lambda by mu is rho. So let's write rho directly. P naught rho to the power k is equal to 1. So P naught is equal to 1 by 1 plus summation k equal to 1 to infinity rho to the power k. Now this is basically rho by 1 minus rho. This is a GP, and the sum of GP is rho by 1 minus rho. So P naught simply becomes 1 minus rho. So P naught is equal to 1 minus rho. That is the value of P naught. Now in the light of this knowledge, let us derive the value of the average customers. N bar is equal to P naught is 1 minus rho. So let's put 1 minus rho. Summation k equal to 0 to infinity k rho to the power k. Now this is a AGP, arithmetico-geometric progression. 1 minus rho k, so 1 minus rho plus 2 rho square plus 3 rho cube up to infinity. Now in class 12 you have probably seen the trick to solve this, so you just do here. S is equal to, I am doing in the side, S is equal to rho plus 2 rho square plus 3 rho cube, so on. Now you just multiply and shift. So rho S is equal to rho square plus 2 rho cube. You multiply by rho and shift one column. So 1 minus rho S is equal to rho plus rho square plus rho cube. Now this becomes a simple GP. This is rho by 1 minus rho. So S becomes rho by 1 minus rho whole square. Implies S becomes rho by 1 minus rho whole square. So this becomes 1 minus rho into rho by 1 minus rho whole square. So this becomes rho by 1 minus rho. Now this becomes N bar is equal to, so the average number of customers is rho by 1 minus rho. So if you put rho, lambda by mu, you will get lambda by mu minus lambda. So this is the average number of customers. So we have derived N bar is equal to lambda by mu minus lambda. Now average time spent by a customer. This will be N bar by lambda. So this will be 1 minus mu lambda. And what is the waiting time? Average waiting time average waiting time is basically, what is the average time spent? This is basically waiting time plus service time. So you do two things. You first wait for your turn and then you get serviced. Waiting time plus service time. So what is the average waiting time? It will just be, this is T bar or T, let's just write T. T minus the service time, T service. So this is TW. T. So this is 1 by mu minus lambda. And what is T service? 1 by mu minus 1 by mu. Since service rate is mu, so T service, the time spent by time spent for servicing one packet is 1 by mu. So this is lambda by mu minus lambda. Sorry, lambda by mu into mu minus lambda. So and average waiting time becomes lambda by mu into lambda by mu into mu minus lambda. And what is lambda by mu minus lambda? Let's write this lambda properly. What is lambda by mu minus lambda? N bar, average number of customers. So this becomes n bar by mu. So total time is n bar by lambda, and out of that waiting time is n bar by mu. So this is the basic expressions for MM1Q. Now we have done the basic expressions for MM1Q of waiting time, service time. Who is there? हेलो, हाँ बोलिए, हाँ बोलिए. नहीं, क्या हुआ? अरे ना ना ठीक है, कंपनी में है, समझ सकते हैं. हाँ ना 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 ठीक है ठीक है, अरे कोई बात नहीं, कंपनी में है, समझ सकते हैं. मैं भी ना 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 ऐसा कोई नहीं है, लोड मत लीजिए, कंपनी में है, समझ सकते हैं, कोई प्रॉब्लम नहीं. ठीक है ठीक है. हम्म ना 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 कोई प्रॉब्लम नहीं है. और बाकी सब ठीक है ना? हाँ ठीक है ठीक है. हाँ ओके. हाँ 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 क्या, हाँ बोलिए बोलिए. अरे वो पेटेंट सबमिशन को लेके था, तो सबमिट हो गया, तो कंप्लीटेड मार दिया. हाँ हाँ ना 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 वो बहुत पहले बनाया था, अभी बस याद आया तो बंद कर दिया. हाँ हाँ ठीक. हाँ 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 बस. Okay, so sorry for the interruption. So as we were saying, sorry for the interruption. So as we were saying that we have derived the average basic parameters of, who is there? So we have derived the basic parameters for MM1Q, and now we know the average waiting time, average number of customers, and we can also find the mean and variance of this customers. So variance of this number of customers. So we know the mean is lambda by mu minus lambda, and the variance of the number of customers in the system is sigma n square, that is rho by 1 minus rho whole square. You can take it as a homework to derive this. So how you will derive the variance of the customer, number of customers. Now we have the waiting time and everything else. So we have mm1q. Now we will go to the next topic of the day, that is network topologies. So for network topologies, we will consult Behrus-Farhausen, Data Communications and Networking. It is one of the most standard books in this field. And for queuing theory, we have used Leonard Kleinrock queuing systems. So I will write the name of the books. It is already given in the NPTEL lecture material, but still I am writing it. For switching, you will study, for switching, telecommunication switching, you will study Digital Telephony by Bellamy. Digital Telephony by Bellamy. The author's name is Bellamy. Bellamy. For the queuing part, queuing theory and traffic part, basically queuing theory and traffic part, traffic analysis. So MM1, Poisson arrival, all this comes under this heading. This one will be queuing systems by Leonard Kleinrock, L. Kleinrock. Again, this is a very standard book. All PDFs can be got from Google, so you can just search the name of these books and you will get it in Google. I cannot share you the PDFs as it is illegal to do so. You have to get it yourself. And then for the data communication and networking part, data communication and networking part, this part we will follow the same data communication and networking. The book's name is Data Communication and Networking by Farhausen, F-O-R-O-U-Z-A-N. So these are the three books you need to study. Now we will switch on to network topology. Yeah. So the main purpose of constructing computer networks is to communicate data. So we have to deliver the data from source to destination with the accuracy and the timeliness. So we have to be accurate in our data transmission. We cannot give inaccurate data at the receiver, and we have to be timely in our delivery. We cannot take infinite amount of time to deliver a packet. And our packet also has to be jitter free. Jitter free means the packets should arrive smoothly. And so here are the five components of a data communication system. So one component is the sender, who wants to send something. Another component is the receiver, who wants to receive something. Another component is the message, the message that has to be sent. Another component is the transmission medium, the medium through which the message will be sent. And another component is the rules or the transmission protocol, means the rules that will govern the transmission of this message from sender to receiver. So if you want to send a letter to your friend or a parcel to your friend, Yeah, you are the sender, your friend is the receiver, that letter or parcel is the message, India Post is the transmission medium or DTDC or Blue Dart, and protocol is basically the algorithms that India Post, DTDC or Blue Dart follow to deliver one message or parcel from one place to another. So these are the five components of a data communication network. So data can be in terms of text. If it is text, then we will of course ASCII code it, and ASCII is a American standard code for information interchange, basically a way to encode characters. Then there you can also send it as numbers, you can send it as images. Images are again translated into bits using RGB or YCM, other kinds of color schemes. And you can send audio data, even that is transmitted to bits, transmitted as bits, and even video data, that is also transmitted as bits. So audio, video, image, number, doesn't matter, everything is translated into bits at the base level. So next is data flow. Data flow is of three types: simplex, half duplex, and full duplex. So you have a stream of bits, that is your data. So if you want to send an image, your data is a stream of bits. If you want to send a video, your data is a stream of bits. Your data will always be a stream of bits. But what is the direction of transfer of these bits? So if you can transfer only from one place to another, A to B, but you cannot transmit from B to A, then it is called a simplex communication. Like between a monitor and a CPU. Your CPU can instruct or communicate to your monitor what to display and what to not. But your monitor cannot communicate to your CPU. So this is a simplex communication. Half duplex communication means at time 1, the one computer will send to another computer. In time 2, that is after time 1, the computer 2 will send to computer 1 in the reverse direction. So both directions cannot communicate together simultaneously. When one direction communication is going on, another direction cannot communicate. So this is not that relevant in computers. This is more relevant in walkie-talkies. So if you talk in a walkie-talkie, like in Puris and other people use, so there you can, if you want to talk, you press a button, then you talk. No one else can talk. You occupy the channel by pressing that button, and then you say over. After you have said something, you say over, and you release the button. That means the channel is now free. Then the receiver, the guy who got the message, will send something in return. He will occupy the channel now, and he will say something, and then at the end he will say over. That's why they say over after communicating in walkie-talkie, like I am at location over, because by over saying over, you are signifying that the channel is now free. You can occupy the channel if you want. But in full duplex, that is in normal mobile phone communication or the communication that we are having currently over Google Meet, there is both directional communication at all times. So you don't have to say over and out. Okay. So this is the direction now of communication. Now we will go to the networks. So what are the criteria for a good network? One is performance. Performance is measured using throughput and delay. Throughput means the quantity or amount of data that the particular device transmits, whereas delay is the time it takes to transmit the packet. So throughput should be high, delay should be low. Reliability is the accuracy with which the packet is getting transmitted, and security means if someone else who is unauthorized, who should not access the packet, can access the packet or not. So the network should be secure, the network should be reliable, the network should have a high throughput, network should have a low delay. So these are the metrics by which a particular network is judged. Now, what the types of connection that we get in a network is first is a point-to-point connection. Point-to-point connection means there is a dedicated link between two devices. So if you have something like this, there is a device here, another device here. So this is, you have a link here, and another device is here, you have a link here. This is a point to point communication, this is a point to point communication, because these links are meant for these two devices only. This link is meant for these two devices only. No other device can access this link. So this is a point to point connection. And a multi-point connection is basically there is a bus and all the devices tap into that bus. So basically there is, say, a server computer and all multiple end laptops. So there is a server in a research lab and there are three researchers. So of course the three researchers won't have three servers of their own. They will just have laptops at their desk and there is a server. So what they do is there is a common link to tap into that server using their own laptops. So this is a multi-point connection. There are multiple laptops but only one mainframe or one server. So this is a multi-point connection. Now we come to the main part of today's topic, that is network topology. So network topology means the way in which the devices are connected. So the term physical topology refers to the way in which network is laid out physically. So it is how network is laid out physically. So like you connect the devices, how you connect the devices, that is the main topic of this. That is the main topic of physical topology. So how you connect the nodes. Nodes means devices. These devices can be laptops, these devices can be mobiles, whatever. So so these devices can be whatever. Now what you have to do is, first we have to go through mesh topology. Mesh topology means the simplest topology. If you have three devices, how will you connect? What is the basic intuition? That you will connect all the devices to each other, right? So here we can see A is connected to B, B is connected to C, A is connected to C. So three devices, they are all connected to each other. So like that, if you have four devices, what will you do? You have four devices. You will do 1, 1, 1, 1. Now diagonals. See, connection done. So you have how many connections? 1, 2, 3, 4, 5, 6. 6 connections. So what is the so like that? Yeah, how many devices you have, that many connections you make. So how many connections you will actually make? You will make NC2 connections if n is the number of devices. Why? Because you have to take, for each connection you have to choose a particular pair. That is, you have to choose 2 devices out of n devices. So that is a NC2 connection. So there are NC2 connections. So NC2, or you can write it as n minus 1 by 2. n minus 1 by 2, like here. So n minus 1 by 2 duplex mode links, connections or links. Now what is the advantage? The advantage is simple. It provides a dedicated path for the traffic. So if devices A, B, C, D, so if devices A and C want to communicate, there is a dedicated link between devices A and C. B or D cannot interfere in that link. So whenever A wants to communicate with C, it can communicate so. And second of all, another advantage is that mesh topology is robust. If the link between A and C fails, that doesn't affect the link between B and D, or the link between A and B, or the link between C and D. All other links are working. So if one link fails, the system doesn't fail. So that is another advantage. And another advantage is of course privacy, because each one of them has a particular link, so they will have a particular advantage of privacy. So mesh topology, in summary, you will have NC2 dedicated links. What are the pros? One pro is availability of dedicated link. What does the availability of dedicated link do? It ensures that there is zero latency. Implies zero latency. And there is privacy. Of course, this does not need any explanation. If there are dedicated links, there will be privacy. And another is the robustness. That is, if one link fails, all the communication does not go down. Just that link fails. So just that pair of devices cannot communicate. So these are the pros and cons. Not scalable. As n becomes very large and expensive. So what is not unscalable? What does unscalable mean? As n becomes large, NC2 grows to, how does NC2 grow? NC2 grows as n square, ON square, right? Because nn minus 1 by 2, if you multiply, NC2 is basically, NC2 is ON square. So n square is a very strong growth. It is a parabolic growth. It is a very strong growth. So as you increase the number of links, your as you increase the number of devices, your links grow as ON square, and it becomes very tough to implement such a network. So a mesh topology might be good for 2 or 3 devices, but it is not good for 20 devices, or it is not good for 1,000 devices. You can only do 1000 C2 and see how large that is. Next, we will go to, what is the next topology? If mesh is clear, star topology. In star topology, basically, there is just the opposite of this. Star topology, there is no dedicated link. There is a hub. This is star. There is a hub. All the devices are connected there. D1, A, B, C. This is called a hub. So, how many links? If you have 3 devices, you need 3 links. If you have 5 devices, you need 5 links. So you will need just n links. Pro, cheap to make. It is cheap and scalable. Because it only has a big O of n growth. So big O of n growth is manageable. And then it is cheap and scalable. And what is the disadvantage? Disadvantage is over dependency on hub. So if the hub goes down, network goes down completely. And if one link fails, link fails, device does not communicate. Device goes incommunicado. It just does not communicate anymore. Because whatever communication it has done, it will do through this link only. So if this link fails, B is dead. So this is star topology, and you need n links. Next, you will have bus topology. And bus topology is similar to star topology in the sense there is a thick cable called bus. So all information travels through bus, and the devices A, B, they will all tap into this bus. C. So they will all tap into the bus. So again, the disadvantage is that it is over. How many links you need? N links. So this again grows as ON. And it has the same pros and cons. What are the pros? It is cheap and scalable. And what are the cons? Over dependency on bus. There are other pros and cons, but since this is a problem solving session, I won't go into that much details. Over dependency of over dependency of bus. Next, last is the ring topology. This one is the cheapest to make. You just have a single wire and the devices just tap into that. And they usually are equipped with a repeater. This repeater basically just amplifies the signal. So this is a repeater. Device A, B, C, D. So this is a ring. So if A wants to pass a message, it will first send to B. A wants to pass a message to D. Say A wants to communicate to B, D for Delhi. What it will do is it will circulate a message either in clockwise or counterclockwise direction. Let's say all the communication happens in a clockwise direction. Then A will pass a message to B. Now B will check whether this message is meant for it or not. If not, it has a repeater. It will amplify the message and send to D. Now D will check whether the message is for him or not. If not, then it will pass to C, and if yes, then it will take for itself. It will take the message for itself, and it will, of course, no longer repeat and pass it. So basically, you pass the message along till the right person decodes it. So what are the pros? The pro is that it is cheap to implement, and signal boosted because of repeater. So signal will always boosted. Signal will always appear boosted, so it will not suffer from lack of power. It will not. The signal will not easily die down. Now, once that is out of the way, the this is cheap to implement, and signal is boosted because of repeater. What are the cons? What are the disadvantage? One, lack of robustness. Why is this not robust? Because if one device fails, the entire ring fails. The entire ring fails. So if one device will fail, if not one, sorry, two, if two device fails, the entire ring will fail. Because if say B and D fail, then this path becomes inaccessible. So if this path becomes inaccessible, A cannot communicate with C anymore. Right? A cannot communicate with C anymore. So this is the lack of robustness is the main disadvantage of ring topology. And another is lack of privacy, because the message is getting accessed by all the devices in the ring till it reaches its rightful owner. So there is no guarantee that the sender will send the message directly to its next neighbor. So it might send to a receiver that is not his next neighbor. So then what will happen is it will go through various handlers till it reaches its receiver, and that compromises the security of the message. Now we have covered all the basic topologies of network. Now we will move on to problem solving. So this is the assignment for week 6. So this is not this year's assignment, of course, that you have to solve according to your own. But let us take the first example. This is a previous year assignment. So let us take the first example. Here, how many cables are required when 20 devices are connected with hub in star topology? So what is star topology? Star topology, you have a hub and devices A, B, C, D are all connected. So how many cables are required? See here you have 3 devices. So how many cables did you need? 1, 2, 3. For each device you need one cable. One cable for each device. So for 20 devices, 20 cables. So correct answer is B, 20 cables. Next, internet traffic follows exponential distribution. We know traffic follows. What does traffic arrival follow? Quotient. So traffic arrival follows quotient. So what is in exponential? Exponential is the inter-arrival times. The times between two arrival, the time length between two arrival is exponential. But the arrival itself, the traffic itself is Poisson distributed, not exponential. So the statement is false. The statement is false. Next, consider a single, let's move this around a bit. Yes. So consider a single server queue with infinite buffer space. The inter-arrival time is constant and is given by 1 second. So the service time, the inter-arrival time is 1 second. The service time required by each customer is always 0.5 second. So what is the service rate, arrival rate? Arrival rate, the inter-arrival time is 1 second. So arrival rate is 1 by 1 second. So 1 per second. So arrival rate is 1 per second. Next, you have service rate. So service rate is 0.5 per second. Now, the thing is, there is no exponential or Poisson distribution. what happens when you do a Poisson distribution like an MM1Q is that the packets might arrive after some time. So even if the mean inter-arrival time is 1 second, doesn't mean every second there will be a packet. There may not be a packet for 3 seconds. Then there might be 3 packets in 1 second. But on an average, it says that 1 packet will arrive in 1 second. But here, there is no mention of any distribution. So the inter-arrival time is constant. So every 1 second, it is determined that 1 packet will arrive. Guaranteed. There is no random process. It is guaranteed that at every 1 second there will be 1 packet. And whenever the packet arrives, it will be serviced by the server for 0.5 seconds. So let's take a timeline. Here, from 0 second to 1 second. At 1 second, there will be a packet arriving. Right? This is arrival. And in the below, there will be departure. Okay. Now, where will the packet depart? This packet number 1, say x1. This packet will depart at 1.5 because after arriving at 1, it will go to service. And service rate is 0.5 second. So, at the middle, it will depart. But no other packet has arrived. The next packet will come at 2. So, this is time. At 2 seconds. At 2 seconds, next packet will arrive, x2. It will again finish service at 2.5. So this is 1.5. It will finish service at 2.5 and it will exit. Next packet will come at 3 and it will exit at 3.5. So see, every packet that is coming is seeing an empty server because 0.5 per second before its arrival, the packet is getting serviced and leaving the queue. So before every arrival, a departure already is happening. So no packet is ever waiting. Whenever a packet is coming, it is finding a empty server and it is immediately going to service. So no waiting time. So everyone is guaranteed to get service immediately. So no waiting time. W is equal to 0. So the correct answer is A, 0 second. Next. Let PF denote the probability of failure of a link in a network. Assume that links fail independently. We say that a network fails if any one of the nodes cannot reach another node either directly or through other nodes. What is the probability that a network fails for a star network with n nodes? So, for one link failure, the probability is given to be PF. PF is the failure probability. And one link is failing independently of other links. So, it's not like one link is failing and then if one link fails, the others have to fail. All links are failing independently if they fail at all. So we say a network fails if one of the nodes, any one of the nodes, cannot reach any one of the another node directly or through other nodes. So if two nodes in a computer, two nodes in a network cannot communicate with each other, the network has failed. If any pair of nodes cannot communicate with each other, we say the entire network has failed. So whatever may be, the network has always to provide the basic communication between all the devices. So now what is the probability that this network failure will happen for a star network with n nodes? Now for a star network, you see, let's take it to the board. Yes, for star network, there is a hub and there are multiple devices connected. Now, A, B, C, D. If any one of the links fail, all can fail with probability PF. If any one of the links fail, say this one fails, then let B can't communicate with A. Communicate with A. So since one pair has failed, entire network has failed. Implies entire network has failed. So just one event with a probability PF leads to the failure of the entire network. So the probability of network failure is P is, what is the probability of this? PF. Just one failure. So PF. The correct answer is PF. One failure leads to the failure of the entire network. So if any link fails, the node attached to it gets disconnected from the network. A star connection requires least number of links to connect all nodes at the cost of increasing probability of failure of the network. So here is the main funda of this star network. That star network is very cheap to implement, but it has a very high probability of failure. Just one link needs to fail for the entire network to go down. Next, calculate the same probability of network failure for ring topology. Now we go to the same funda we have to do for ring topology. For ring topology. Here in ring topology, you have devices. Let's take a 4-device ring topology. A, B, C, D. Now, if the link D fails, just the link D fails, then can A communicate with C? Yes, A can still communicate with C. Can A communicate with D? A can communicate with D. Can A communicate with B? Yes, A can communicate with B. So D individually, the D's link has failed, but still communication can go on. But when you say, like, to give you a better example, I think another device is needed. So or let's say like this. Now B's link also fails. Two links failed. B's link also failed. Now what happens is, since B's link has failed, this repeater has failed, this repeater has failed, both failed. So A cannot reach C. Previously when D failed, A was reaching through B. When Delhi failed, A was reaching through Bombay to C. But now Delhi and Bombay has both failed. So A cannot communicate with C. A-C communication. Even though their links didn't fail, their communication failed. Similarly, if you add another device, you will still see You only need two failures. So in the language of graph theory, so if you compose a graph out of this, you will see that you need the minimum cut set that disconnects this graph to make a failure. So here you need to choose a pair and two nodes have to fail. So if there are n devices, if n devices are there, then how many ways can you choose this number of devices? Number of device pairs. Number of device pairs is NC2. So you choose one of the NC2 devices, right? Two of the NC2 devices. You choose two of the you choose one of the NC2 pairs. So you choose two devices in one of the NC2 pairs. Now, what is the probability of these two links failing? The probability of the failure of this link is PF. The probability of failure of this link is PF. The probability of failure of this link is again PF. And they are independent of each other. So, probability of network failure will be NC2 PF square. So it will be of the order of PF square. So the correct answer is C. So a ring gets disconnected when two links fail simultaneously. And the correct answer is C, PF square. Now, what is the maximum propagation delay for a ring network with n nodes of radius r? Assume n is even. So what is the maximum propagation delay for a ring network? So there is a ring network and there are n devices or n nodes and the circle of the ring is r. The circle radius is r. So 1 minute. So assuming n is even, so there are an even number of devices, nodes are placed equidistant from each other and speed of light is denoted by c. So now you have a ring topology. You have a ring topology. Ring, so like this. Let's take it as a circle and let's take 8 devices. Now let's name them clockwise: A, B, C, D, E, F. Now they are not equidistant, but please assume they are equidistant. So this is a circle with a radius of r. Now if A wants to reach B, it will have some distance d. If it wants to reach C, that will be 2d. If it wants to reach D, it will be 3d. If it wants to reach E, the distance, if this distance is d, this distance is suppose d. So the distance between A and B is d. A and C is 2d. A and D is 3d. A and E is 4d. A and F is 5d. No. A and F is again just 2d. So, oh, sorry, there will be a device here. I have missed that. Sorry. So this will be F. This will be G. And this will be H. So this will be D. A and B is D. A and C is 2D, 3D, 4D. F is 5D, but it will not go in this direction then. It will go in counterclockwise direction. And in counterclockwise direction, F is just D, 2D, 3D. So it is just 3D. G is again 2D, H is D distance. So what is the maximum distance? This is D distance from A, this is 2D, this is 3D, this is 4D. Again you go 3D, 2D and D. So you see that the maximum distance is from A is E. Similar analysis if you do, from B is F, from G is C. That is, whenever you go to a device, whenever you go to a device that is diametrically opposite to the device you are currently sending from, if the sender and receiver are diametrically opposite, then you need the maximum distance. Maximum distance is when equal to sender and receiver are diametrically opposite. Opposite. So if sender and receiver are diametrically opposite, that means what is the distance between them? 4D. So what is 4D? That is half of the circumference. So 2 pi r by 2. Right? So this is pi r. 2 pi r is the circumference, by 2 is pi r. So what is the time? Maximum delay? Maximum delay is pi r by c. Distance by velocity is time. So pi r by c. Done. This is pi r by c. Correct answer is option A. Now, here this is a single server queue and this is a MM1. This is MM1 system. This is a classic MM1 system. For the system shown in figure 7a, the inter-arrival times of customers are expected to be exponentially distributed with 1 by lambda is 2 seconds, and the single server queue with infinite buffer space. The service times are exponentially distributed with mean 1 by 2. So service times are, so see, inter-arrival is exponential. Inter-arrival is exponential means this is m. Service time is exponential. This means another m. And there is a single queue, single server queue, so 1, and infinite buffer space. So this is a classic MM1 queue. Okay, so this is a classic MM1 queue where lambda is half, mu is 1. So 1 by lambda is 2, that is lambda is half and mu is 1. Now what is the mean response time? That is the total time t, total time t. Now if you look at our derivations, you will see total time t is given as 1 by mu minus lambda. We have done the derivation, right? I am not doing the derivation again, so you can check. The total time t is this. T is, let me, t is so t is n by lambda, n bar by lambda. So this is 1 by mu minus lambda. 1 by mu minus lambda. So we will just put the formula here. So t is equal to 1 by mu minus lambda is equal to 1 by mu is 1 and lambda is 0.5. So 1 minus 0.5. So 1 by 0.5. So this will be 2 seconds. So you will spend 2 seconds. The correct answer is D. D for Delhi. So 2 seconds. Now consider figure 7b. So what's in 7b? 7b, the packets arrive, but then they are dispatched to 2 independent MM1 queues. So instead of one single MM1 queue, there are 2 independent MM1 queues, and the packet are dispatched into any one of these 2 with a particular probability. So The system consists of two single server queues, so two MM1 queues, each with infinite buffer space. Customers are randomly distributed to each queue with an equal probability. So the probability of going to a queue A, like this queue, the probability of going to this queue is half, the probability of going to this queue is half. Both are half, equal probability. Now, the service times are exponentially distributed with 1 by mu equal to 2. So mu is again half. The mean response time is. So the packets are arriving at a rate of lambda equal to half per second. And the service time is now also half, mu equal to half per second. But the packet arrival to each queue is not half. This is the total lambda, total arrival. Now, only half of these packets are going to a particular queue. Only half of packets are going to, let's say the first queue is QA. Packets are going to QA. Are going to QA. So, for QA, that is the first queue, what is the effective lambda? Effective lambda is not half, it is half of half, that is 1 by 4. 1 by 4 per second. So one packet arrives actually in 4 seconds for QA. So for QB also the same parameter, lambda b is equal to 1 by 4. Now, and what is the mu? Mu is for A and for B, both are half. Now what is the average response time? That is the time spent, average response time. Is 1 by mu minus lambda. So 1 by 0.5 minus 0.25. So this will become 4. So waiting time is 4 seconds. Correct answer is option A. Now, again we consider single server queue with infinite buffer space. The inter-arrival time is exponentially distributed. The service time is also exponentially distributed. So this is again another MM1 queue. MM1 queue. Now here the lambda, inter-arrival time is 1 second. So lambda is 1 per second. And mu, the mean the mean service time is 0.5 seconds. So mean service rate is 1 by 0.5 or 2 per second. So what is the mean waiting time? Now see, it is not the mean response time, it is the mean waiting time. So waiting time, mean response time is equal to mean service time plus mean waiting time. So mean response time, this is what we were calculating till now, mean response time. This is the sum of two parts, mean waiting time, and mean service time. So what is so TW plus TS. Now T is 1 by mu minus lambda. This T, this is the T, our mean response time, 1 by mu minus lambda. And what is mu? Mu is 2 and lambda is 1. So 1 by 2 minus 1. So this is 1 by 1. So 1 second. And what is the service time? Service time is simply 1 by mu. So 1 by 2 or 0.5 second. So what is TW? TW is waiting time, T minus TS. So 1 minus 0.5. This is 0.5 second. So half a second. Now the correct answer is 0.5 second. Now in question 10, internet service provider has 4 dial-up ports. Connection requests follow a Persian arrival rate with of 3 requests per hour. The session duration of each connection, the request, is exponentially distributed with a mean of 1.5 hours. What is the probability that a connection request will be rejected? Okay, so here there are 4 dial-up ports, and their packets are coming at a Persian arrival, and the arrival rate is 3 requests per hour. So this is basically a traffic model, Erlang B traffic model. So basically you get 3 requests per hour and there are 4 ports. So what is the session duration for each connection? So once you get the connection, you will have 1.5 hours of connection time. So once you connect to the dial-up, you will be there for 1.5 hours. So what's the probability that a connection request will be rejected? So it will be rejected if all the 4 ports are busy. So it has a buffer capacity of only 4, not more than that. So it is MM because Poisson arrival and exponential service. 4 because there are 4 servers, 4 dial-up ports. 4 because why is there are 4 here? This is the queue capacity. This is the server number of servers. This is number of servers that we already know, MM1. What is different here is this is the queue capacity, because it won't have more than 4. Now here the rate of arrival is 3 requests per hour, 3 per hour, and the rate of service is 1 by 1.5. So 1.5 hours the service goes on, so 1 by 1.5, so 2 by 3. So the traffic intensity A is equal to lambda by mu is equal to 3 by 2 by 3, that is 9 by 2 or 4.5. 4.5 Erlangs. So if the offered traffic is 4.5 and there are 4 trunk lines, so the blocking probability you can get from an Erlang table. Blocking probability is given as B 4.5 comma, you can calculate this or you can just consult our Erlang table, comma 4, because there are 4 servers. So B 4.5 comma 4. So you use the Erlang B table. If you don't worry, if you get this in exam, you will be provided with the Erlang table. So Erlang B table, and here is the Erlang B traffic table. The offered traffic is 4.5. So offered traffic is in the center. So that is 4.5. So what is the nearest offered traffic that you can see to 4.5? And the number of trunk lines is 4. So 4 with 4 trunk lines, what is the offered traffic? When does the offered traffic reach 4.5? It reaches 4.5. Wait, 4.5 now. N is the number of servers. Blocking probability in percentage. So the 4.5 is reached for 4 trunk lines. 4.5 traffic is reached in somewhere in between 30 and 40. So you can write 35. So somewhere in between 30 and 40. So 30 and 40 means 30, you can write 35. So 35%. So how to read the Erlang table is basically, see, this is the probability percentage. This is percentage. B is in percent. B is the blocking probability. It is in percentage. So this is 40% probability. And this is the number of trunk lines. 1, 2, 3, 4, 5. These rows. And this in the middle, the table entries, the columns are blocking probability, the rows are trunk lines, and the offered traffic is in the table. So here you have 4 trunk lines, so you will obviously concern yourself only with this row, only with the highlighted row here. Now in this highlighted row, your offered traffic is 4.5, so it is somewhere here in between 3.8 and 5.0. So it is somewhere between 30% and 40%. So you don't know, so you just take what, 35%. So whatever is nearest to 35%, you tick that option. So here you see this is 49%, this is 65%. Both of them cannot be correct. So because the thing is, I know that my blocking probability is somewhere between 30 and 40. So the only correct answer is 0.3567, that is 35.67%. This is 35.67%. So only this is correct. So correct answer is option E. Okay. So the correct answer is option A, 35%. There is a formula also. This assignment will be uploaded, so you can check. And there is a formula also. So you can consult this, you can put the value in the formula and get the answer. But it is easier to consult the Erlang table. So with this, I will be concluding today's class. Thank you. Please join again at the same time next Tuesday. Bye.